Wonderful. Thank you so much to everyone for joining us today, and especially to our special guest. My name is Emmy Betts. I am the Deputy Director for the Program for Injury Prevention, Education, and Research at the Colorado School of Public Health and the School of Medicine. And with the help of Lucia Turpak, I direct this Research2Practice seminar series. In these sessions, we really like to focus interesting and innovative ways of looking at injury prevention, incorporating evidence and research, and hopefully impacting injury prevention practice wherever it may be. And I am so excited for today's talk. No pressure. Today we have Dr. Allison Anderson, who is an actual aerospace engineer. She is an assistant professor in aerospace engineering at the CU Boulder campus, with a focus in both human performance, as well as she does some work in spacecraft habitat design and the environments in which humans spend their time while in space. And I don't know about others who are listening in, but recently I have particularly felt the desire to escape. So I'm looking forward to maybe, at least for the next hour, thinking about escaping the planet. We will have time for questions probably at the end, but please put your questions in the Q&A box, and we'll be gathering them for Dr. Anderson at the end. And the session will be recorded. The link will be sent to you, to participants after the talk. And with that, I'm thrilled to turn it over to Dr. Anderson. Thanks.
Thank you very much, and thank you to everyone who is tuning in or will be watching the video. Today, I'm going to be talking about injuries that occur while working inside of the spacesuit. I'm going to be covering not only the injury and incidences, but also talking a little bit about the engineering of the spacesuit, because it's fundamentally coupled to the way in which injuries occur in that environment. I'll talk about the exciting work that NASA has been doing to really focus in and try to mitigate injuries. And I'll also talk a little bit about our own research in the bioastronautics lab at CU Boulder to try to mitigate some of these issues. When we think of astronauts living and working in space, oftentimes images of individuals working in a spacesuit come to mind. This iconic image is from the Apollo 11 landing of Buzz Aldrin, and you can see Neil Armstrong in the reflection of his space shield. And the spacesuit has come to embody humanity's desire to explore and do science, and is really thought of as something that is culturally defining as we explore and extend our boundaries. However, what often people are not often thinking about the fact, though, that rather than seeing this as a garment, it's really a technology and a piece of hardware that sustains human life when working in extreme environments. In fact, the fundamental purpose of the spacesuit is to protect the human. It's to ensure the health and safety of the individual inside. There's sort of two core paradigms that I'll introduce. So the first is during launch and entry activities where people are wearing spacesuits, or intravehicular activity, or activities that occur inside the spacecraft, but also during spacewalks, which I'll be referring to as extravehicular activity, or EVA, which again are activities that happen outside of the spacecraft. And the reason why individuals wear spacesuits in these two paradigms is that they're often considered some of the most dangerous portions of the mission, so therefore help to protect the individual when working under those circumstances. And despite the fact that we've been working on these technologies and thinking specifically about high altitude pilot suits that have been iterated upon for around 80 years or so, they've been designed to accommodate our anthropometric dimensions and to build in flexibility such that people are able to work inside of them. But despite all of that, we still see that individuals get injured while working inside the spacesuit. One of the fundamental reasons why it's so hard to mitigate those injuries is that, as with all things that go to space, it's also coupled to its engineering requirements. So it's heavily driven by the mission requirements, the influence of prior design, which has been demonstrated to be safe and to have the longevity needed to work in space, and as well as the resources associated with, for example, taking up additional mass or something like that. So before I move on to talk about what are the primary risk drivers for injuries that occur inside the spacesuit, I wanted to provide a little bit of a disclaimer, given that I'm talking to folks whose core expertise is in injury, which is that for the purposes of this talk, I will be referring to injuries more broadly, in the sense that I'll be really be referring to any reportable incident that occurs inside the spacesuit that could be related to an injury. And so in some instances, this may not meet the true clinical definition of an injury. In fact, there's been a huge amount of discussion at NASA to really define what is a clinical injury that occurs inside the spacesuit and what are the core criteria associated with that. But I'll be referring more broadly to any sort of reportable injury incident. And it's also worth noting that a lot of the times that folks work inside the spacesuit, they may also be associated with pain and discomfort, and that's less well documented. There's been huge efforts at NASA to increase documentation. So I think that the data sets that we have are increasing in size as well as in subtlety, but really often a lot of historical information about pain and discomfort is really only associated with some experimental work that's tried to capture that. So I wanted to provide that disclaimer, given the fact that I'm an aerospace engineer talking to folks whose core area of expertise is injury. So with that, let's dive into some of the categorizations of spacesuit injury risk. There are really two core paradigms where we think about injuries that occur inside the spacesuit. The first is during training, and the second is during the mission. Training is often underappreciated as a phase in which individuals get injured. But specifically thinking about injuries that occur during EVA, it's actually very critical to be keeping track of how injuries occur. The reason for that is one of the best ways for astronauts to train in preparation for performing their EVAs is in the world's largest swimming pool called the Neutral Buoyancy Lab. This facility enables the astronaut to be working inside the spacesuit and made neutrally buoyant. So I don't know if you can see my mouse, but despite the fact that this spacesuit is pressurized with air, they place weights around the body to evenly distribute mass such that they can be neutrally buoyant and able to perform all of the core operations and to practice for the activities they'll be performing on their spacewalks during the mission. There's two primary reasons why this can be injury inducing. The first is that while the spacesuit is made neutrally buoyant, the person inside is not able to be made neutrally buoyant. So in this particular circumstance, the individual is inverted. So even though the spacesuit is maintaining its location, the person inside would be shifted towards the shoulder end of the spacesuit, which can be quite uncomfortable. The second is that there is the viscosity of water that would also not be present during microgravity. Sorry, my nephews are. That would also be present during, wouldn't be present during microgravity, that causes individuals to have to exert additional level of effort in order to overcome the viscosity of water. During the mission phase, we often think of extravehicular activity as the primary time in which the spacesuit is worn, and it's the portion of the mission where individuals, who have been training in the Neutral Buoyancy Lab then execute those activities. But there's another entire category of spacesuits that get worn during launch and entry, or really during the dynamic phases of flight. Here I'm showing some individuals working inside of the Orion spacecraft, preparing and training, and they're wearing a launch and entry suit. So I will be focusing most of my talk on work that happens inside of the EVA spacesuit, but I'll briefly touch also on some of the work that's been done to mitigate injuries during launch and landing. When we think about then the subsequent injury types that result from working in these three environments, we often, the primary categorization for injuries are associated with repetitive use due to working in the EVA spacesuit in the Neutral Buoyancy Lab, as well as during extravehicular activity. And then we also see that acute injuries can occur while working inside the spacesuit during launch and landing. However, due to the nature of working inside, even for EVA, there can also be acute injuries that occur, for example, by trying to get in or out of the spacesuit while in preparation for training for in the neutral buoyancy lab, or even during extravehicular activity, particularly thinking about injuries that might occur, say, on a planetary surface, for example. So these are the ways in which we categorize injuries that happen inside of the spacesuit. So I'll briefly touch upon injuries that occur in launch and landing, and then we'll return back to extravehicular activity. So IVA suits, their core function is to help keep the crew alive in off-nominal events. They can sometimes be referred to as get-me-down suits, and you often see them, for example, in the image on the right, as astronauts transition to and from their spacecraft. And so they have their origins in suits that were worn for high-altitude pilots, and in fact were the kinds of spacesuits that were worn during the Mercury program. But their primary core design drivers are that we try to minimize the amount of hard components that are present in this suit in order to reduce the load that might impact the person upon launch or landing, or during an abort. Another primary design driver is that they must be comfortable when unpressurized for long periods of time. And then finally, they often are at a much lower operating pressure than the spacesuits that we use for spacewalks. However, even at these pressures, they can still become stiff and rigid when pressurized. So here's an example of an astronaut who is wearing their launch and entry suit. And you can see that this individual, first of all, has some stiffness and rigidity around the limbs, as well as they're not seated perfectly inside of the suit, given that the suit is not conformal to the body. And you see these issues as well for extravehicular activity suits, which I'll talk about in a second, but I wanted to highlight the fact that this is something that is true for IVA suits as well. And in fact, these suits are often built such that they have a nominal posture. So I love this picture because these two cosmonauts and astronaut are holding their, actually it's an ESA astronaut, a Russian cosmonaut and a US astronaut, sorry. So they're all three holding their Sokol suit, which is the Russian IVA suit. And you can see that even when the suit is pressurized without a person inside, it looks like it's sitting. And they do that in order to ensure that when worn in an off-nominal circumstance, that the legs don't extend in an undesirable way, and they're able to still control the spacecraft while wearing this suit. And there's been actually a huge amount of research done, particularly more recently when thinking about dynamic phases of flight, including launch, abort, and landing, primarily because we have so many new spacecraft that are coming online. So on the right, I'm showing a picture of the Orion capsule under parachuted landing. And in particular, Jeff Summers at the NASA Johnson Space Center and his colleagues have really developed some risk limits associated with injuries during dynamic portions of flight. And then there's been some great research out of the Wake Forest Center for Injury and Biomechanics that is also focused on the kinds of dynamic loading using both computational modeling as well as anthropometric test devices in order to understand what those injury loads would look like. So I don't have time to do justice to this entire body of literature, but I did definitely want to acknowledge that this is another area where a lot of folks are doing great work. However, what I'll be focusing most of my talk on is EVA and how injuries occur inside of this type of spacesuit. Most of the work that's been done up to this point has really been focused on looking at microgravity EVA, or EVA that happens when during the shuttle missions or on the International Space Station when the shuttle was flying, and then also more recently for the International Space Station. But as we make plans to return to the surface of the moon, there's been a lot more attention paid to the kinds of injuries that occurred while the Apollo astronauts were exploring on that planet's surface. So as I discussed before, EVA is any activity that occurs when the individual is working outside the spacecraft. In the past, EVA has been used for a wide variety of reasons, including doing technology demonstrations, constructing habitats to repair a spacecraft item, or even for contingency situations or repairs, as well as to explore the surface of the moon. The US spacesuit and the Russian spacesuit and even the Chinese spacesuit, those are the three EVA spacesuits that have ever flown, are incredible pieces of technology because they really provide everything the person needs to stay alive. They're the world's smallest human-rated spacecraft and do an incredible job mimicking our own natural environment as much as possible. There are multiple health risks associated with performing an EVA. As I mentioned before, it's a highly choreographed, complex activity. And fortunately, there has never been a major incident in the US that's ever led to loss of crew life, but there have been several close calls. You may recall from the news the water intrusion that happened with Luca Parmitano while he was doing his spacewalk with Chris Cassidy. Fortunately, they were able to maintain control of that situation and it resolved positively, but there have been a couple, let's say, close scrapes. And obviously, these are incidences that we would really like to avoid. The major health risks that I'll be talking about today are primary injury, obviously, but also that is associated with fatigue, and that is coupled as well with the problem of decompression sickness. So I'll talk through those three in a little bit more detail in the next couple slides. But I also wanted to acknowledge that there are other health risks associated with EVA. For example, the exposure to radiation is increased as you leave the protective walls of the spacecraft habitat. There's also the risk of equipment failure. On the right, I'm showing a glove breach that actually occurred when the glove rubbed against a burr while working on the International Space Station. And then finally, dust irritation, specifically as we think about lunar dust, which was reported to be highly irritating for any mucous membranes like the nose and the eyes, as well as for respiratory issues. But returning to how injury, fatigue, and decompression sickness are coupled, again, it's all tied to the engineering of the spacesuit. So what I'm showing in this figure is a slide that on the x-axis shows, so this figure shows the entire sort of trade space of potential atmospheric composition for the environments that are used in space. On the x-axis, I'm showing the volume percent of oxygen, ranging from 0% oxygen, which would obviously not be habitable for humans, all the way up to 100% oxygen. On the y-axis, I'm showing total pressure, and these are in your favorite units if you prefer metric or English. But the green line shows what's a normoxic equivalent. So we can see up here in the top at full atmospheric pressure, we have approximately 21% of oxygen, just like we have here on Earth. And this is the atmospheric composition that the space shuttle was usually maintained at, that the International Space Station is currently maintained at, and the Mir Space Station was maintained at. And all along this line, as you can see, as you decrease the total pressure in the spacecraft, we also have to increase the percent oxygen that's made available to the human in order to maintain normoxic conditions. On the lower bound, we're seeing the blue line, which is the point after which below that you would have a hypoxic situation. So that creates the lower bound of what we would be able to achieve. And then the upper bound is driven by oxygen toxicity. Now, when we think about, this figure shows spacecraft habitats where they fly along this chart. But actually, when we plot spacesuits on this chart,
Dr. Anderson, we lost audio, I think.
Oh no.
Just check. There you go. Wait, I think it's back on.
Can you hear me now?
Yeah, that's great.
Okay, great. Thank you. Okay, so when we plot where our spacesuit pressures are on this graph, so the current US spacesuit is called the xEMU, and that's maintained at 4.3 psi. And the Russian spacesuit for EVA is called the Orion spacesuit, and it's maintained at 5.8 psi. And so we can see here that actually these two spacesuits are maintained at 100% oxygen, but they're actually in sort of the upper envelope of what might be considered acceptable. So the question is, why would you have an elevated pressure if you, when you could have it potentially be lower? And the real reason for that is to mitigate decompression sickness stress. So decompression sickness is the presence of symptoms associated with bubbles that come out of solutions, specifically nitrogen bubbles, as the inert gas that's dissolved into our tissues. So when you go through pressure transitions, this causes the stress on those inert gases and causes them to come out of solution. So in the event that that occurs, you run the risk of having decompression sickness. So if you are transitioning from this 100% 1 atmosphere of pressure to approximately a third of an atmosphere of pressure, that actually represents a decompression gradient that runs the risk of causing decompression sickness. So as a result, it's desirable to have elevated spacesuit pressures in order to mitigate the DCS stress and also to reduce the operational overhead associated with getting nitrogen out of the human body. So prior to performing a spacewalk, astronauts, depending upon the protocol that they use to remove nitrogen from their body, might have to stay for several hours, breathing 100% oxygen, performing light exercise, trying to remove the nitrogen from their body before they transition to this 100% oxygen spacesuit environment. And so it's desirable for DCS reasons to have an elevated spacesuit pressure, but it's highly undesirable to have a high spacesuit pressure due to mobility constraints. So every spacesuit that has ever been flown has been pressurized with gas. So to maintain the physiologically relevant pressures that I discussed in the previous slide, the fabrics that make up the spacesuit become stiff and rigid. So I want to be clear, this figure that I'm showing on the right is not at all meant to pick on Final Frontiers design. They're great colleagues of mine. They do excellent spacesuit design work, but I like this figure because it shows the strain that this individual is going through in order to try to perform an elbow bend. Now, this is an IVA suit, but really every spacesuit, because they're pressurized with gas, and they're made out of fabric materials, have the same fundamental limitation in that it is difficult to bend these pressurized fabric environments when they are at these pressures. And once we did the initial development on the spacesuits that eventually took us to the surface of the moon, since that time, the vast majority of development on spacesuit, specifically the pressure garment of the spacesuit, has really been focused on increasing mobility in order to mitigate these issues. What I'm showing on this slide is an expanded view of the Extravehicular Mobility Unit, which is the current US spacesuit. And I show this because, first of all, I think it's beautiful to see how this incredible system is engineered, but I also want to focus on just how many additional accommodations must be made in order to try to create a mobile system at those pressurized levels. So you can see each of these different elements where you see seams or areas of different patterning. These are areas where pleats and bellows have been intentionally built in to allow the human to induce buckling in the spacesuit as they try to move their arm. And so these are done particularly around the joints in order to increase mobility. You'll also see areas where we have these hard metal rotational bearings to connect different spacesuit components. And these are useful because along those rotational bearings, they're nearly frictionless, but the downside being that they are they also create rotational movement only along that plane. And then the last thing I want to highlight in this figure is that, at least in the United States, we've adopted a philosophy of a modular component in order to accommodate sizing. So humans come in various shapes and sizes, and in order to accommodate all of us, you can add certain sizing rings or multiple different sizes of, say, for example, the arm assembly, small, medium, and large, in order to try to swap out different components in order to accommodate people of different sizes. And so while this is a very effective way to ensure that the entire range of from the 5th to 95th percentile ranges of human anthropometry can be accommodated, it does create issues associated with having that idealized perfect fit. And so these three issues coupled together, the need to have a physiologically relevant reducing the stress of decompression sickness leads to a certain pressure window. That pressure window then impacts the mobility of the spacesuit, and the mobility of the spacesuit ultimately has the potential to lead to injury. And so, as you can imagine, this is a very challenging environment to work in. So, for example, tying this back to some of the injuries that occurred during training, on the right here I'm showing one of the Hubble repair missions that occurred. And for every hour of EVA that was planned to be performed on the Hubble, there was up to 12 hours of EVA in the training environment of the neutral buoyancy lab. So this is a huge amount of accumulated time working inside the spacesuit. And as I mentioned before, there have been many studies that have documented the degree to which the spacesuit causes injuries to those who are wearing it. What I'm showing here is some seminal work from Schuring and Strauss. And although these data are outdated now, they do provide, they're some of the best representations of the kinds of injuries that we see, and just to really help us get a sense of the ways in which injuries occur while working inside of the EVA spacesuit. So Schuring categorized all of the reported injury incidences in space, and Strauss performed a study where he tracked for several years the kinds of injury incidences that occurred during training. And we can see one specific trend, which is that in both on orbit and in training, the hand, the foot, and the shoulder are the three dominant areas where we see the majority of our injuries. So the reason why biomechanics are altered inside the spacesuit is coupled to this pressurized habitable environment, where we can categorize the way in which biomechanics are altered by thinking about programming. So programming is the way in which the spacesuit moves along those planes of motion, specifically when thinking about a spacesuit that has multiple bearings. Indexing, which is the position of the human relative to each of the specific suit components. So a good example of that would be if, for example, you have the right size of the spacesuit elbow, but your elbow is shifted relative to where the spacesuit's elbow joint is, then that can cause a biomechanical mismatch. And then the externally applied joint torques associated with that pressurization that's causing the rigidity. So those issues kind of coupled together all lead to the fact that experienced EVA astronauts will often talk about the fact that they have to relearn how to move while working inside the spacesuit. So they'll learn new movement strategies in order to accommodate the fact that the suit doesn't move like they themselves would move naturally. As we know, though, of course, fatigue can lead to people, let's say, not following those relearned movement strategies. And it's very difficult to remember that you can't just reach up and touch, the top of your visor, that you have to instead roll your shoulder out and then perform an elbow bend in order to execute that action. I wanted to show a couple of pictures here also of what the indentation. So again, these are really focused on the injuries, but also wanted to highlight the fact that that there are also indentations that can also occur as a result of pressing up against the spacesuited components. So if we really map this to things that we can deal with design, for example, adding accommodations to the stiff pressurized structure versus compatibility, so fixing the way in which the person is referenced relative to each of the elements and then also getting them to the right size, then we can hopefully design out some of these spacesuit injury potential problems. I wanted to highlight those top three injuries really quickly, just to kind of give you a little bit more of a deep dive into what those three specific injuries look like. So the first one I wanted to focus on is, sorry, my figure is not animating here, but the hard upper torso. So the hard upper torso is the hard upper shell of the xEMU, and actually I can circle back to a picture of what that looks like after the talk. But essentially, it is a fiberglass shell against which all the other spacesuit components are mounted. And it comes in primarily extra large, large, and medium. The size small has never actually been flown. But this spacesuit element, one of the core reasons why we think that the this element has the potential to cause injuries is related to the way in which people are able to articulate their shoulder while wearing it. So particularly we think about the planar hut, which is the hard upper torso that doesn't have the ability to accommodate additional movement through a rotational bellows. So when we think about normal shoulder abduction, we see that, and this is an animation that was derived from some research done by Williams and Johnson, which is sort of the seminal work on spacesuit shoulder injury. We can see that this action occurs through 3 different joints and 1 articulation. Whereas if we then impose upon that the hard upper torso and specifically the shoulder ring, we can see that actually the movement is impeded, and rather the glenohumeral joint, where we start to see the shoulder recruitment in order to accommodate a certain movement, we can see that that becomes over recruited, and that ultimately can lead to rotator cuff tears, slap tears, slap lesions, and there's also been several individuals who have reported having shoulder pain due to inflamed bursa at that location through over recruitment of the shoulder joint. There are other additional factors that are believed to be related to this, not just the hard upper torso, but also how that interplays with individual anthropometry, the amount of time that people are given to train as well as recover from working in these spacesuit hard upper torsos, as well as whether or not they've had any prior shoulder injuries. And so while this is not the most commonly reported injury, it can be the most debilitating and has resulted in over 20 shoulder surgeries for astronauts, which then, of course, impact the rest of their training regimen. Another one of the very common injuries that's reported are hand fatigue and issues. One specific injury that's of note is fingernail delamination. This is caused by the fact that because the gloves are also pressurized, they're also stiff and rigid, and so as a result, you have the hands can become fatigued, and you have an over recruitment as people try to grip within the spacesuit gloves. This is also exacerbated by the presence of moisture. So if you think about it, because the spacesuit is trying to protect you from the environment of space, it also keeps all of your moisture buildup in. And although the liquid cooling ventilation garment, which is a comfort garment that's worn underneath the spacesuit, does have ventilation tubes that can possibly extend all the way down to the wrist, it's often reported that the hands do have an increased amount of moisture, which then contribute to the softening of the nail and ultimately can lead to the fingernail delamination issues. Another injury issue that I wanted to highlight is spacesuit boot fit. Now, this is not true. So while boot fit and discomfort has been reported in training and in on orbit, the spacesuit boot fit problem that I'm referring to here is actually something that is not of core concern for microgravity operations. So here I'm referring to the need to walk in the spacesuit, where because you are driving the spacesuit internally with your leg, we actually see that the heel lifts up out of the back, and that's been reported in ground-based studies. You can see a figure on the left from some research done where they asked test subjects to walk for 10 kilometers on a treadmill, because that's sort of the design requirement for how long they would have to walk back in an exploration scenario. And there were blisters and severe discomfort reported as a result of that. So you can kind of think about it, if you were walking in a pair of hiking boots that were too large for you, how that repetitive rubbing would ultimately lead to skin-based injuries as well. And so heel lift is something that the next generation planetary surface spacesuits are going to need to mitigate, and is something that is going to be of concern as we think about people walking around in their spacesuits. Now, obviously, NASA is well aware of what the environment for the spacesuit looked like, and so they've developed a lot of hardware in order to mitigate some of these concerns. So what I'm showing here on the left is, on the right, in both figures on the right, is the liquid cooling ventilation garment. I referred to that in the last slide, but essentially what this is it's a conformal elastic garment that has water tubes snaked through it, and those water tubes absorb the heat of the individual. But on top of that, they also provide a mounting structure for padding. So there are thin Teflon strips that can be added to the liquid cooling ventilation garment in order to provide an additional layer of padding. You can see it actually implemented here on Steve Robinson, who's about to perform an EVA. So you can see those same strips sewn over his shoulders. They also have these ventilation tubes. These are the yellow tubes that you can see on his arm here that are meant to try to decrease the amount of moisture accumulation in the spacesuit. The hard upper torso also has a harness that's supposed to mitigate shifting, as well as comfort gloves. But it has been reported that each of these devices, while important to maintain comfort, have been limited effectiveness in order to actually mitigate injuries. So I want to emphasize, though, that NASA has been very dedicated to reducing injuries. So they have realized, particularly as a result of the, sending many more diverse individuals into space, as well as for longer durations and to perform some of the most complex EVAs since, for example, constructing the International Space Station or repairing the Hubble Space Telescope, that they really have been able to zero in on what some of these injury mechanisms are. So for the next generation spacesuit, they've put a huge amount of time, money, and effort into improving and quantifying their designs in order to mitigate injury risks. So they've been using statistical shape models that are derived from actual astronaut body scans, as well as through using military databases associated with human anthropometry, as well as doing experimental investigations in order to ensure that all different anthropometries are accommodated through the spacesuit redesign that they've been doing. They've also been very proactive about trying to mitigate injury through prospective data collection for example, by performing experimental studies, which they often collaborate with universities in doing that, which I have personally benefited from. But they also have increased their data collection in order to also help quantify the problem and use that information to move forward. And so there have been a plethora of both experimental and theoretical studies that are really geared towards understanding the spacesuit injury problem. So I won't go through each of these studies specifically, but just to highlight the fact that they're focused on each of these injury mechanisms that I've already previously described through both experimental and modeling-based evaluations. So just to give you a highlight of how NASA is thinking about moving forward with their new advanced concept spacesuit designs, this is the Orion Cruise Survival Suit, or the OX suit. And I think this is a super cool IVA spacesuit because it really pushes the limits for what IVA spacesuits have really ever done. So this spacesuit has some incredible design requirements. For example, being able to sustain 144 hours of pressurized habitable environment, which is just well beyond what a lot of other traditional IVA suits have done, as well as for an 8 psi contingency situation, again, to try to, for a limited period of time, be able to try to mitigate the amount of decompression and stress that astronauts might be performing in if, for example, something, like an Apollo 13 type situation where we had an incident on the way to the moon and we had to keep them in their suits as their primary survival mechanism for long periods of time. It, and you can see also at the shoulder and specifically and at the hands, they've done a lot of work to try to improve the degree to which this suit has mobility, again, to acknowledge the fact that it could potentially be used for long periods of time. They also have recently announced their, or I guess shown to the public, their xEMU design. And xEMU is really the exploration EMU, where the EMU is the current US spacesuit. And the incredible thing about this spacesuit is that it was really fundamentally different in terms of shoulder mobility, as well as rotational mobility about the hip and the legs. And so this suit has a rear entry philosophy that allows for a greater degree of operational readiness when thinking about moving towards planetary surface explorations. They've just done a huge amount of iteration and development on this particular spacesuit, and it's really been exciting to see some of that work that's been in development for many different years kind of come to fruition in this final spacesuit design. So just to highlight a little bit of the work that we have been doing for spacesuits within my group, because I think this is really an exciting time for human spaceflight. And within our research group, some of our objectives are to really understand human and spacesuit interaction in order to then subsequently improve the design of hardware and to kind of contribute to the efforts that have been mentioned here. So we're doing this through developing wearable in-suit sensors, to also develop technologies that can allow us to mitigate injury, and then finally through advanced spacesuit concepts. So some of our prior work has developed in-suit pressure sensors in order to measure the actual pressure contact that happens on the arm. So what I'm showing here on the right, these data are 6 different sensors that were mounted on the spacesuit arms, the locations of which are shown on the left figure. And then at the top, I'm showing synced in real time, this individual performing an action called the crossbody reach. And by aligning temporally the ways in which these pressure sensors were activated, this allowed us to not only for the first time to characterize what the contact pressures between the human and the human's body and the spacesuit were, but it also allowed us to track the location of the person's arm inside the spacesuit. For example, you can see that as the person performs the elbow bend in order to reach up and touch their helmet, we see all of the sensors on the lower forearm being activated. And so this allows us to have a window inside the suit to really see how sensors that get around some of the primary issues with other inertial sensors that get mounted on the body to measure joint angles. So one of the primary issues with inertial sensors for spacesuit applications are their form factor, durability, as well as the fact that they often use magnetometers, which because the magnetic environment isn't static, can actually induce error rather than fixing error. It's a technique that's often used in inertial sensing in order to reduce error. So we've been building from the ground up some inertial measurement unit systems that can be mounted on the body in order to measure joint angles. Again, allowing us to then take that information and model and understand how the person is moving inside the suit. We've also been using 4-dimensional motion capture in order to measure foot morphology in 3 dimensions as well as over time. And we've now taken these data and converted it into a statistical shape model that allows us to use anthropometric information as a predictor for how to design spacesuit boots better. But despite all of the recent and incredible work that has gone towards mitigating injury for thinking about moving to the planetary surface, in my opinion, I believe that as we transition to Mars, it's going to be important for us to really rethink spacesuit architectures from the beginning. For example, exploration paradigms for a human mission to Mars call for 24 hours of EVA per crew member per week, which is just a huge increase in the amount of EVAs that really have ever been performed, let alone in a fashion that would be almost every other day. And so this is just an incredible jump in capability from where we currently are with the way in which astronauts are performing spacewalks. And on top of that, you're going to be highly constrained even more for a Mars mission by mass, volume, and thermal considerations. And so, I've spent a lot of time talking about gas pressurized spacesuit, but I haven't really, acknowledged the fact that there are other spacesuit architecture concepts. So I wanted to briefly go over those, and then I'll wrap up with some work that we've been doing. So I've talked a lot about gas pressurized spacesuits. They are incredibly robust, proven technologies that we know allow us to get the job done. But I've already mentioned some of the potential design constraints associated with them, such as inhibiting mobility, causing fatigue and injury, and the fact that if you were to have a rupture of the material, that you would potentially have a catastrophic loss and failure. Now, I'm sort of cheating because this figure here on the right is not a fully gas pressurized spacesuit like the EMU. In fact, it's a hybrid suit with a hard spacesuit. So a hard spacesuit is a concept where rather than having any of those fabric components, then it's actually a sequence of fully hard elements that are linked through multiple rotational bearings. So one advantage here is that you have constant volume as the individual moves, which means that you have very reduced joint torques. And so the individual will be able to not be fatigued as they were working inside this suit. One potential or several potential concerns with these designs, though, is that because the motion is achieved through these rotational bearings, that it can create unnatural biomechanical movement. Further, these suits can't be collapsed in the same way that gas pressurized suits can be, thus necessitating the need for a greater degree of mass, stowage volume, and then that they must be individually tailored for a single person rather than having the modular design philosophy that current gas pressurized spacesuits have. The third spacesuit design philosophy uses mechanical counterpressure. So this spacesuit philosophy essentially circumferentially compresses the body in order to create the physiologically relevant pressure that the gas would otherwise be providing. So some advantages to this concept are that it allows for enhanced mobility, has low volume and mass, and has the potential for increased safety, in the sense that if you had a pressure rupture, you would be able to, essentially use almost like a tourniquet type device in order to recover up that region of the body and maintain pressure. However, the primary challenge is that these spacesuits for full body suit have never been demonstrated at the pressure that would be needed in order to perform an extravehicular activity. There's also difficulty associated with putting them on and to taking them off, as well as to maintain a constant pressure around the entire body. So one of the things that we've been working on at CU Boulder is the hybrid spacesuit concept. So this spacesuit combines a layer of mechanical counterpressure with a layer of gas pressurization, and thus together combines to create a suit that would essentially reduce the engineering requirements on both sides of that equation, has the potential to increase safety through redundancy, and if you were able to create elevated pressures above that original window that I had showed you, then you could also decrease operational overhead. And so we've been trying to develop this suit in order to overcome some of the other potential design concerns, such as how do you maintain pressure at the seal, for example, at the neck seal, and then also how do you deal with increased system complexity. So the ways in which we've been trying to deal with that are to characterize the ways in which gas pressurization affects movement, as well as to develop some mechanical counterpressures, but prototype gloves. So one of the things that we've done is to look at how linearly increasing the level of gas pressurization that's been applied causes performance decrements on a complex task. So this is called the modified Purdue pegboard test, where individuals turn these U-bolts 90 degrees twice in a clockwise fashion. And so we found that as you linearly increase spacesuit pressure, that you actually get an exponential decrease in performance. So they it took our test subjects much longer to actually perform these tests, which implies that if you were to operate the spacesuit at a lower pressure, you would gain much larger performance advantages than if you were to, say, only halve the pressure. We also have done some work to quantify the pressure that's been produced with some of our mechanical counterpressure spacesuit glove prototypes. And so one of the challenges for spacesuit, for MCP gloves, is that oftentimes it's difficult to actually characterize the amount of pressure that's being placed on the body. So we had to develop a pressure sensing glove and wear that inside of our spacesuit prototype glove in order to understand what actual pressure was being applied to the hand. So in conclusion, spacesuits are a key element to enable human spaceflight as well as human space exploration and science. IVA suits are primarily, the injury risks are associated with dynamic loading in launch, abort, and re-entry. EVA spacesuit injury risks are primarily associated with the pressure, indexing, and fit associated with how the individual is wearing and working inside that spacesuit. And then that training injuries are also a critical component to consider. NASA has been hugely dedicated to understanding and mitigating injury risk, but my personal opinion is that as we move towards a Mars-like exploration paradigm, that we should also be considering alternative spacesuit architectures. So with that, I'd like to, of course, acknowledge all of my graduate students who have contributed to this work, all of the other mentors that I've had along the way who also have contributed to some of the data that I showed, and then as well as my colleagues at NASA, David Clark Company, and some of the resources that I used for pulling pictures of what I think are beautiful spacesuits. I guess I'd also like to acknowledge my nieces and nephews and my brother-in-law who are doing construction while I am giving this talk. And then lastly, I wanted to provide an opportunity to take questions and show some really cool, what I think are really innovative and interesting spacesuit concepts.
Oh, wonderful. That was so fascinating. Thank you so much, Dr. Anderson. We'll open it up to the chat box first, but I'm going to take my moderator privilege to ask one first, which is, you touched a little on sort of the difficulty in different anthropometrics and different astronauts. And I know particularly there's been some discussion about gender and women astronauts, and there was a big to-do, I remember, when there weren't enough suits for 2 women to do a spacewalk together and so forth. And I'm just curious sort of how, well, two-part question. So one, besides height, are there other considerations like distribution of body mass that would affect overall suit design? And then also, I'm just curious, not for myself, because I've missed my window, I realize, but how much do they take into account sort of astronaut body size or compatibility when they're preparing a mission?
Sure. So I'll talk first through the first half of your question. So yeah, this is often a question that comes up, what happened with the first all-female spacewalk that had been planned? And I think that there's like a little bit of a subtlety in the argument that I think is important to note. And it really gets back to the design choices that we made towards spacesuit sizing. And so because we've gone, so in the United States, the philosophy around astronaut selection, actually this does get into your second question, has been, to be expansive in the size and shape of individuals that we can take, such as to allow things like performance and skills to really be the driving requirements for how we select astronauts for certain aspects of the mission. So in that particular instance, there is no such thing as a male spacesuit or a female spacesuit. But it's definitely true that when the spacesuit was originally designed, that the astronaut corps was not as diverse as it currently is. And so, because we haven't had, say, for example, like the space shuttle, which allowed us to take a lot more mass up to the International Space Station, there's only a certain number of spacesuit components that are aboard in order to do that mix and match philosophy in order to accommodate multiple different shapes. And so if I recall correctly, I believe the issue was that, when you take the different components and reconstruct the spacesuit, you have to go through a huge amount of time and safety procedures to make sure that the spacesuit has been put together correctly and that the person who's going to use it will be safe. And so one of the astronauts had experienced a smaller spacesuit than she had originally been training in and found that that was the right size for her. And the next astronaut who was going to be performing that spacewalk with her was going to be using the same size. And so they kind of had, for lack of a better term, let's say it was like a medium and a large, and they really needed 2 mediums. And so in order to take apart the large and reconfigure it into a new medium, that would have been just like a huge operational burden. So that's why they had to like revise that. But so, so there's really like that aspect of it. Now, NASA has focused very specifically on doing a better job of accommodating smaller sized people when thinking about the xEMU. In fact, the image that I showed of the woman who's wearing the spacesuit was, in the small configuration, and she was able to do all of the mobility that you would want out of a spacesuit, particularly when thinking about trying to do geology and exploring the moon's surface. I think I touched on all aspects of your question, but
yeah, I think you did.
Remind me if I forgot something.
Great, and if there are any openings, you could give me a call. Next question is around vision and the role of vision in injuries and particularly visual limitations from the helmet risk. I'm wondering if you could touch on that. How much is that a factor in terms of increasing the difficulty of tasks, or is it really more the motion?
So I'm not sure, I haven't read the question that you're referring specifically to. So there's kind of, I'll answer this in 2 ways. So one of the, so field of view associated with the astronaut being able to see their workspace. So the helmet is not conformal to the body. So it is mounted to the heart of her torso and the head moves inside the helmet. The new redesign in the xEMU uses is intended to have a larger field of view, so it has a elliptical shape to it. And in fact, it was so big that I believe they had to go through a redesign to actually even make it smaller because it was actually too big for the astronauts, at least during training is my understanding. But regardless, that trying to have an expansive field of view is a critical design driver of that particular system. I'm not sure if the question was also geared towards the idea of the spaceflight-associated neuroocular syndrome, or SANS, which is the issue associated with astronaut vision changes that have happened during long-duration spaceflight for an unknown etiology, but essentially it causes visual acuity changes. I have not heard of any particular issues that have arisen associated with those vision adaptations, but you could imagine for a long duration mission that, you know, should vision become degraded, that yes, that would be impactful. But you know, if they have a limited field of view and mobility is restricted, then you lose situational awareness around the work site, which could potentially be problematic. So they've also tried to mitigate that by adding what's called informatics. And so the idea here is that they're collecting much more data and distilling that into a usable form for astronauts to be able to, you know, in the next generation spacesuits, be able to have much more information readily available to them. It's not going to be like the Iron Man type display, but you know, the idea, let's say it's inspired by that.
That's great. I think the question was more about like head mobility, but I didn't even know about the neuroocular changes. So maybe I don't want to go to space anymore. So two more questions have come in. So one from Jay Lemery, fantastic talk. And he asked, could you talk in a big picture sense about how those of us at the Anschutz Medical Campus can support the work that you all are doing in Boulder?
So I think that Colorado as a state has just a huge interest in the aerospace industry and specifically in the space industry. And there are exciting opportunities that are in the works for actually developing the potential for a joint degree program where folks who really have an interest in the medical side of things could also potentially get a master's degree in bioastronautics, which is the area that I work in, you know, in sort of like a joint degree fashion, in the same way that there are other, you know, Masters of Public Health, MD programs. So we would like to be able to establish something like that, because it is true that since human spaceflight is an environment where a lot of the health concerns are fundamentally derived from the fact that we've engineered a space for people to live, that coupling those two disciplines together is something that I think is super valuable. And so that's one way in which we've been doing that. And also both of our campuses have released opportunities for trying to increase research that happens across, in addition to some of the work that we've been thinking about for the academic side of things as well. So I think that's another potentially really interesting opportunity, is to take some of the research medical expertise. You know, I would love to be able to put in a grant with someone who really focuses in on injury mechanisms and think about how that relates to some of the engineering work that we do around spacesuit injuries.
Well, wonderful. We will certainly keep you in touch with our group for sure. Last question before we end. This is from Dr. Carol Runyon. Are there efforts to adapt the spacecraft to suit characteristics, or is it always the other way around, that you're adapting suits to the spacecraft environment?
The amount of time historically that we've spent doing spacewalks is just so much. It's just so much less time than all of the other work that is done in the spacecraft to live and to work. Now, there have been some concepts, one of which I'm showing here, actually two of which I'm showing here in these last sort of somewhat silly images, but this idea of, you know, for deep sea exploration, they've used a lot of small habitable volume submarines that have end effectors that allow people to go to depths that would otherwise not be possible, and to use those end effectors as a way to do their work in a concurrent, in the same location manner. And so there has been some work to, instead of thinking about the spacesuit as this anthropometric system that's meant to mimic the human, but rather to kind of think about it in the, you know, like the hyper small spacecraft concept. I personally don't think that will work as we think about specifically Martian exploration. But, you know, because there, you know, we want to basically have our field geologists doing as much exploration as they possibly can. But that would be a paradigm that could be potentially useful, say, for example, if we wanted to send people to an asteroid. I guess the last thing I will say on that is that as we move towards long duration exploration missions, they are planning on decreasing the spacecraft environment down to what's called the exploration atmosphere, which is about 8.3 psi. So that reduces the overall decompression stress. You still have to maintain the spacesuit at the lower bound of that figure that I had showed earlier, but you can definitely then decrease the total pressure because you're no longer stressing individuals going from full atmospheric pressure down to spacesuit pressure. Now you'd be going from, 8 psi down to the 4 psi.
Cool. Fascinating. Okay, and I'm going to sneak one last one in because I don't want to let you go quite yet. And Carol Runyon has another great question. You mentioned deep sea exploration. Are the lessons from developing and improving spacesuits, how are they being applied to other areas like firefighters, or are there other examples besides deep sea exploration where it's being translated?
Yeah, actually, firefighters is a perfect example. So, any environment where you have, specifically thinking about some of the injury mechanisms that I was talking about, any time where you have body-borne bulk, specifically thinking about firefighters or any individuals who are wearing protective devices, such as military service members who have large packs and or body armor, as well as police officers who may have vests that they're wearing. So anytime that you have a lot of on-body bulk that can change biomechanics, but also the loading that changes also changes the biomechanics by changing the posture at which people are working, you can generate a lot of some of the same issues. So actually, there is a lot of crossover to think about how can, for example, some of the modeling techniques that we use to understand human spacesuit interaction, or some of the pressure sensors that we use to understand human spacesuit interaction, how does that translate to any of these other terrestrial environments where we still have people who are living and working and doing, we care about human performance in extreme circumstances. It just happens to be a different way in which their performance is being decremented.
Oh, fascinating. I am so grateful to you for your time and for giving this fantastic talk today. I thank you on behalf of the Program for Injury Prevention, Research and Education, and I certainly hope we can continue collaborations in the future. Thank you to everyone who joined us. Our next seminar is going to be sometime in September. Stay tuned for the date. We've got some great sessions coming up related to transportation safety, elder abuse, and domestic violence. So be safe out there, and thank you again, Dr. Anderson.
Thank you very much for having me. I really appreciate it.
Take care. Bye.